Okay, so we're at worksheet 24, and there's a whole bunch of classic modeling problems. So in theory, you shouldn't have to watch this video, but in reality, you probably do. What I'm going to do is show you some warm-up things to get your brain going, and then I'm going to give you some hints on the specific questions on your worksheet. So first of all, we have the kind of question where, let's say we have a wall. You have one of these in the worksheet, and then you want to put some kind of fence that's rectangular in shape. So you know you want the shape to be X, Y, X, where it's a rectangle. The two sides that are not up against the wall that are touching the wall but not up against the wall. So this, in other words, you don't need to close this off. That's the deal. The wall gives you some part of your fence. So you have usually a fixed amount of fencing and you want to maximize this area. And so you want to say area is equal to x, y. You want to maximize the area subject to the constraint. The length is equal to 2x plus y, and it's usually fixed. So I'm gonna just make it 100. Okay, so it's whatever the problem gives. So it's just a classic problem, and the only thing that changes is pretty much the wording, but it's really the same problem, and then that number changes. Other than that, it's a classic problem. So the way you go about doing this is you solve, let's say, for y, okay, and then you put that in the area formula. Okay, and then you take the derivative. And then you set it equal to 0, solve for x, and there you go. And I'll let you finish it yourself. But that's the process. So you solve for x, and then from x you find out y, and you multiply x and y together, and then you say, hey, I maximized the area, this was the maximum area. So that's how that problem goes. Okay, another classic problem is if you just say, I'm going to use the same 100 or whatever length, in this case is 100, and I'm going to make a whole rectangle. So what ends up happening, well, I'll show you. It happens the same every time. So the only thing that changes with this problem is he changed the length, and then the area is going to be xy, and we know that the length is 2x plus 2y. So easily we know that y, so you divide everything by 2, so x plus y is 50. Y is 50 minus x. And so the area must be x times 50 minus x, which is 50x minus x squared. Take the derivative. Set it equal to 0, and you can go from there. Okay, but that's exactly the same thing we just did, except with a missing y because you're up against a wall. Okay, those are very, very classic problems. You should be able to practically do those in your sleep. Okay, next one. Okay, I just wanted to point this out, this diagram in one of your questions. So I didn't do a perfect job of recreating it, but I want you to understand something, that if I actually made my semicircle correctly, I can take any point on my semicircle, and here is supposed to be a radius, that this thing is automatically 90 degrees. Okay, that's a cool theorem from high school geometry that you probably forgot or never learned. So you have actually two options for this problem. You can either drop a perpendicular here and split this into two triangles like the instructions suggest. Then you have two right triangles with area 1 and area 2, and you can find the areas and add them. Or you can just find this distance and multiply and divide by 2. The other thing that you should realize is that since you're just trying to maximize this, you're trying to maximize the area of this triangle, that my pen doesn't want to help me here. You're trying to maximize the area, so you could maximize area squared, or you could maximize 2 area or 2 area squared. So my recommendation is to maximize 2 times area squared. And the reason why I think about this geometrically, let's say we have this length A and this length B once you figure it out. So A times B is actually, well, I should give it different letters, sorry. There's too many letters here, P and Q. So P times Q is going to be twice the area you want, but who cares, because you're still maximizing the same thing. But if you wanted to maximize this squared, all you have to do is actually say P squared times Q squared, rather than trying to take the square root. Okay, so this is the thing I'm suggesting that you maximize. Anyway, if you do it geometrically, it should be pretty obvious to you what's going on. So I just want you, I'm going to draw a couple, and you can make the inference yourself. I won't say it. But here's one particular option. The blue one is another option. The red one is another option. And I want you to sort of look with your eyes and figure out which one you think is bigger. What is going on here? What is the obvious optimal triangle if you want to have the biggest area? Okay, so you can answer that yourself, and that's the geometric solution. And then you should be recreating this same thing using calculus. But oh, by the way, even if you know the answer, it won't be enough to do the quiz, because what I actually ask you on the quiz is something like, I'll give you an x value. You have to find the y value, and then you have to find the area. So you have to go ahead and do some of those calculations, even if you found the optimal triangle already. Okay, one of your questions asks you about a closed cylinder. And so what this means is that the bottom is closed, the sides are closed, and the top is closed. So what you need to think about is in terms of, let's say you've got yourself a radius and a height. You have a top and bottom, which is pi r squared, and you've got two of them. And then you've got this thing, if you think about a soup can label and you open it up like that, and what is the surface area of this soup can label? And I think you'll agree that it has to be the circumference of the circle, which is 2 pi r times the height. So it's plus 2 pi r h. Okay? So is going to be the total surface area. That's the lids, the two lids, and this is the side. Or you can say top and bottom. Okay, so that's the formula you probably need to know. The other formula you need to know is volume, which is the top being pi r squared times the height, which you probably didn't have any trouble with that. You probably didn't have any trouble with that one either, but it just looks a little intimidating sitting there, and you may think, do I really need to take the derivative of that thing? And the answer is, yeah, you do. You do. But by the time you take the derivative, you will have done some other manipulation to it to make it a little more palatable, but yeah, pretty much. Okay, so what have we got? We've got ourselves circles, okay? And let's start with a unit circle. I'm just going to sort of build up so you understand how you write ellipses. The unit circle is x squared plus y squared equals 1, okay? And sometimes we write it y is equal to plus or minus square root of 1 minus x squared. So you should be able to recognize it in both of those formats. But I'm going to focus on this format for now. Now, if you dilate this thing, so you enlarge it, so maybe it's 10 on either side, now r squared is 100. So we should think of this generically as if we're going out from r to r, then what we're going to get is r squared. Okay, now let's have a slightly different situation. Now if we take this guy and we squeeze it down or stretch it by some amount. So let's say we wanted to turn it into an ellipse. We're going to stretch it or squish it somehow so that one of our axes is going to get knocked off. So I'm going to call this, instead of R and R, I'm going to call them A and B, let's say. I might regret calling them A and B. But let's say, for example, we replaced x with x divided by, let's say, q, and let's say we replaced y with y divided by r, and by doing that well, let's make it p so I can leave the r squared. So we took our circle and squished the x-axis or stretched it, or we squished the y-axis or stretched it. Okay, so now we have an ellipse, but having the r squared here is kind of annoying. So if you think about what happens algebraically, this is just an algebra thing. So when you see an ellipse, you'll understand kind of the reasoning behind it. Why we don't use an r squared here for an ellipse, except now we have too many letters floating around. So if we had, x squared over q squared plus y squared over p squared is equal to r squared, that would be a pain. And so what we usually do is we just divide everything by r squared, whatever that would have been. And then the r squared becomes 1. And that way all this stuff gets wrapped up. And so now we have a new way of saying it, x squared over, well, I don't know if this is the same a and b, so I just don't want to worry about that. X squared over a squared, y squared over b squared equals a is the way you typically see people write ellipses, because all that garbage gets combined. Okay? So in your exercise, one of those letters is a 1. So let me just make up another problem that's similar but different. Let's put a perfect square here and a perfect square here, just because it makes the calculations easier. If you had an ellipse, and you had the formula for an ellipse, and you wanted to know what it looks like when you plot it, then what you can do is first of all say, well, what if y equals 0, then x is clearly plus or minus 4. So plus and minus 4 works as long as y equals 0. Then we go the other way and we say, well, what if x is equal to 0? Well, y can be plus or minus 5. And if I drew the ellipse the wrong way, then I would just draw it the other way. I got lucky. I completely got lucky. But I could have just as easily put the 25 over here, and then the drawing would have been wrong. And so then I would have had to just stretch it, which I can do because I'm on a computer. Sorry, you can't do that. I guess if you're on a computer, you can. Okay, so I want you to just kind of get a sense for ellipses that way. Okay, and the last exercise in the worksheet has this crazy function, and it truly is crazy. But you have to remember something about e. E to the natural log of a is just a. And so we're going to make use of this fact and rewrite this guy as y is equal to e to the natural log of x 1 over x to the 1 over x. And so now we know this other property of logs that we like, x to some power means you can drop that power out in front. Okay, you can just hop off, like hop off the train, hop off the log train. There you go. Whoops, I meant to say times. Put the equals over here, please. Thank you. All right, so this guy is the same as e to the 1 over x, natural log of x. So now what you're dealing with is you have e to some power with a function inside, but the function inside is an f of x, g of x situation. So you have a product rule inside your chain rule. So you have a chain rule, which is e to some function of x. Okay, so that means you have a chain rule, but then you have q of x is equal to 1 over x times natural log of x, so this guy is the product rule, okay? That should be enough hints to get you going. Sometimes you just need to have a little nudge in the right direction. I think the rest of what you're being asked to do here is straightforward. I will again reiterate that if you're trying to maximize a distance, you can just maximize distance squared. It's a really common trick. So students often say distance equals, and they get some garbage in here. It's really horrible, awful garbage, and then they try to take the square root, and it's all cool, But you may as well just maximize the square of the garbage, because you're still going to get the same maximum, the same critical point. You're going to get the wrong answer, but then you're going to plug your critical point into your same original function. So one way to think of this, okay, I don't even have like a 1 here. Let's say there's a 1 here and a 1 here. So what does it mean if this is the thing we're trying to maximize? Well, really the maximum looks like it's about here. Or maybe it's tied here. But if you square this function, what happens? Okay, pardon my disgusting sketch, but if you're trying to maximize d, you may as well maximize d squared, because it's going to happen at exactly the same places. I meant for this to be up more like this. Okay? It's going to have the same zeros, but wherever d is negative, d squared will be positive. So maybe I should have made it more like this. It flips up somehow. But the point is, anything, it's still monotonic, and everything above the line y equals 1, then the red line is going to be above the blue line, and everything below that, y equals 1 line, then the red line is going to be below the blue line. But it doesn't matter. The point is, it's still always going to be maximized at the same x value. And then once you get those critical points, if you want the actual distance, you just plug it back into that blue curve again. You don't have to worry about that red curve anymore. So this is a very, very common stunt we use when we're trying to maximize distance. We always just maximize distance squared, because it's just a lot easier. One more thing I wanted to sort of give you some food for thought. One of the questions you're going to be asked is, given this ellipse situation, you're going to have a point somewhere inside or possibly even outside the ellipse, it doesn't matter, and you want to know what the point on the ellipse that's closest to the given point, what is the distance to the ellipse. And you're going to go ahead and calculate the distance formula and minimize it and everything. But I want you to kind of just visualize what's going on. And there's going to be some kind of tangency here on the ellipse, but what you're going to actually be aiming for is you're going to be aiming for sort of like a normal here. I'm having trouble drawing this, but let me think of it this way here. Okay, so if there's a point on the normal right there, and if you draw a perpendicular right here, I don't know why my pen never wants to cooperate with me. There we go. So all the points on this line right here are closest to this given point. So I'm going to make it in yellow. Okay, this yellow point here is the closest point on the ellipse for all these guys on this straight line. So you're kind of sticking a dagger through the ellipse. And that's going to be true all the way around the ellipse. So I want you to kind of imagine like some kind of dagger with, some kind of dagger that's shaped like this. That's a bad picture. I'm thinking of a dagger. And I want you to think about sticking it into the ellipse at a right angle. And that's going to give you a good visual for all those points which are now closest to that given point. Okay, that's enough of a hint, I think, because if you just plug and chug your way through the calculus, and you're going to get an answer that doesn't make any sense. So one of the questions that has to do with the ellipse, you're better off trying to understand the geometry and answer it geometrically, rather than just plugging and chugging through the calculus and getting a completely bogus answer and then thinking you did something wrong, when really you didn't do anything wrong, but the process itself is subject to failure sometimes. So go ahead and do it, get the ridiculous answer, and then say, oh wait, this must be the one she wanted me to do geometrically, because the geometry always wins. So anyway, that's your clue for that question. And I think that's all you need to get through worksheet 24. And I will see you in class. Take care.